go ahead and record down here. Start recording. Because some people actually do like to look at these after, later. All right. All right. So we have iodine pentafluoride ion with a -2 charge. And we've added up 44 valence electrons, and we say, you know what? All right, so we're going to put the iodine in the middle because that's the one all by its lonesome. And we say fluorine, 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 fluorine. We make bonds, a bond being 2 electrons. And we'll do the same thing in your labs. All right, and that's 5 of them, so that's what, -10 gives me what? 34 left over. That was 10, right? 5 times 2, 10. Okay, 34, and then we have 5 of them, and 5 times 6 is 30. So we'll put another 6 up here, so we'll go 2, 4, 6, 2, 4, 6, 2, 4, 6, and don't skip these steps. It's very tempting to just, start slapping them down there and just, putting in dots and going for it. You really do need to subtract them off and things. So did I do that right? That's 30. That was 5 times 6. 5 times 6 is what? 30, right? 5 times 6, and that leaves me with all right, 1, 2, 3, 4, 5 times 6 is 30. Yeah. No, 5. Yeah, it is 30. So that would leave me with 4, right? And so that would give me 1, 2, 3, 4. And there it is right there. And now we've got 1, 2, 3, 4. And we've got this hypothetical monster with 7 things around it. Okay. Which I don't have a geometry for. But that's how we'd do that one. All right. Now, let's say that we had water. And we go through the whole process of putting together our so what's the geometry of this guy? So we look on pages 350 and 353, and we see how many we got here. We've got 2 bonded, 2 non-bonded. So what's the geometry for this? And we look on page 350, and we see 2 and 2. We look at our table, and we say bonded, non-bonded. Is it page 350? Yeah. 2 and 2, and we see bent. And so this is bent. And if we were to sketch this out, we would just draw it like this. We would say bent, HOH. You see? Okay. And we can do the same thing for, say, let's say ammonia, which we did. But we go through the trouble of NH3. And we go through the trouble of doing the Lewis dots. You can do this on your own, and we end up with this right here for our Lewis structure. So what's its geometry? And so we look on page 350 once again, page 350. But we have to know, how many bonded do we have? We have 3 bonded. How many non-bonding do we have? We have 1 non-bonded. And what is this? This is trigonal pyramidal. And usually we just abbreviate it PYR. PYR. Trigonal pyramidal. Because it's a little pyramid with a triangle base. Trigonal pyramidal. All right. So you have 2 choices. You can either memorize this list, or you can just have the list handy. It's easier just to memorize it. It really is. Okay. And so now the really exciting stuff is with your expanded octets. And let's say you had, let's say you had an iodine in the middle, but you had, say, a fluorine out here, a fluorine out here, a fluorine out here, a lone pair over here, and let's say a fluorine down there. What would that be? And you look at this and you would say, well, I've got 4 bonded, and we'll abbreviate with that B, and we say, and 1 LP, lone pair non-bonding, and we go 4 and 1, and we see that is something called a seesaw. And that's on page, in this case, I'm looking at page 353. All right, now look, now how does this look like a seesaw? And you may say to yourself, I don't see that. And see, but see, here's how you look at these things. You see this right here? That's equatorial. This is axial, going up and down is axial. So this is axial, going up and down, axial. And the way you look at this, and this is how you have to look at these things, you actually have to lay this guy on its side. You have to flip it over on its side. And if you do that, it ends up looking like this. You got the fluorine kind of down on the bottom like that. Okay. And then you've got your fluorine coming off. All I did was lay it on its side, and you can put 2 kids over here. See, here's a person. There's a person. And they're on a seesaw. You see that? They're on a seesaw. They're going back and forth on a seesaw. So, you know, they go this way. They go that way, right? Seesaw. That's why it's called a seesaw. All right? Just like a T-shape. Why is it called a T-shape? Because it's literally shaped like a T once you lay it on its side. Okay? So when we're doing all of these, we're looking at just the atoms as far as the geometry goes. There's lone pairs still in there, though. If I was to put them in here, the lone pair would be right there. All I did was flop it over on its side to get to the seesaw. Okay, now when you are doing the lab, there is this thing called you have this list of bonded, lone pair, and then lone pair. If you've looked ahead on the next lab, you will see that. And these refer to only 90-degree interactions, only 90-degree interactions, okay? So let's take a look at this one right here that was a seesaw. How many bonded would you have that are 90 degrees? Well, I'm going to do this in green just so we can see it. Here's a 90. There's a 90. Here's a 90. There's another 90. Okay, going from axial to equatorial is 90 degrees. You got this is I'm really apologize. I'm trying to do this on a 2-dimensional surface. All right, but it's a 90-degree interaction between axial and equatorial. It's 90 degrees, so that's 90-90. So bonded would be 4. Bonded. How many bonded lone pair interactions do we have? Well, I'm gonna do this in red. And we go, now remember, it's axial, equatorial. Here's 1. Here's another from the other direction. We have 2. Okay. And you may be saying to yourself, well, what about these guys right here? What about those that are on the equator? That's 120 degrees. It's a triangle. It's 120 degrees on the equatorial interactions are 120 degrees. So they don't count. This list up here is for 90 degrees. So there are no lone pairs interacting with lone pairs, and so that's 0. Now here's the thing. I'm going to kind of circle this and drop it over here. There are never lone pairs. 90 degrees for the most stable. Okay. It's kind of like this. If you're drawing molecules or you're trying to make molecules and you end up with lone pairs being 90 degrees, it means you don't have the most stable configuration. That's what it means. Okay, so you won't have lone pairs of 90 degrees. Okay. Also, these numbers up here will only have numbers. These are only for page 353 or 5 and 6 domains. The only way you can have a 90-90 interaction is if you have either trigonal bipyramidal or if you have octahedral. Is the only way you can have 90-90. And what I mean by that, let me start a new page over here, is if we take anything, even if we take like methane, let's take this guy right here, and we say bonded, bonded, bonded lone pair, lone pair, lone pair, right? What do we have for bonded, bonded? 0. Why do I say 0? Remember, this is only 90 degrees. Only 90-degree interactions. Only 90s. But what do we have here? Well, this is 4 bonded, 0 non-bonded. So this thing is tetrahedral, which means these bond angles are 109.5. All of them. 0 bonded, bonded. Because none of them are 90. It has to be 90 for it to be the bonded-bonded interaction. It has to be 90 degrees. Bonded lone pairs is no lone pairs. No, it's 0, 0 all the way down. Let's take water. And if you look at this, this is tetrahedral electronically, but look, this is 2 bonded, 2 non-bonded. This is bent. Okay, I looked on my table, 2 and 2. And what's the bond angle here? Well, it's about 109.5. It's 109.5 all the way around. So once again, bonded, bonded, bonded lone pair, lone pair, lone pair, 0, 0, 0 all the way down. 0, 0, 0 all the way down. Because what does it have to be? 90 degrees. Now, I'm just showing you this for the purposes of the lab. All right. Where do you ever see this in real life? Bonded, 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 lone pair, lone pair. You will never see it anywhere other than right here and only in that lab. Nobody uses this. This is a Dr. McIntyre. Dr. McIntyre is another member of our faculty. He learned this, I guess, at the University of New Orleans or something like that, where they did this, and no one ever does this. Okay, you do this to try to decide what's the better structure. Okay, this is the justification. When you get into page 353, you have to decide what's the better structure. Let me draw something here. Let me draw 2 possibilities. All right, and I'm going to draw this T-shaped molecule here, or which one's better? Okay, and if you look at this, you would say bonding, 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 lone pair, lone pair, lone pair, okay? Just like in the lab, bonded, 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 lone pair, lone pair, lone pair, okay? And if you look at this one, bonded, bonded is what? This is, here's 1, there's 2, okay? This is equatorial for axis, equatorial interaction, and so there's just the 2. Bonded lone pair, there's no 9, there's what do we got here? We've got 1, 2. We have 2 bonded lone pairs, and lone pair is 0. Okay, over here, what do we got? Bonded, bonded. We have 0 bonded. We have 1, 2, 3, 4, 5, 6. And how many lone pairs do we have? We have 0. And you may say to yourself, well, which one matters most? And the way we look at it is most favorable is bonded bonding is more favorable than bonded lone pair, which is more favorable than lone pair. Okay, so we want to maximize our bonded. Which one maximizes our bonded? That one right there. Okay, and lone pair is definitely do not want lone pair. Okay, so this one has too many bonded lone pairs. You with me so far? It's about those interactions. Lone pair interactions are worse than atom or bonded interactions. Now, here's how I learned it at the great University of Georgia. All right, here's how I learned it. If you have 5 domains, lone pairs go equatorial. Lone pairs go on the equator. If you have 6 domains, lone pairs go axial. That's how I learned it. Where are how many domains do we have here on both of these? This is 5 domains. What do we say down here? Equatorial. Where are these guys? Equatorial. You see? They're equatorial. So if I have something like this, and we have a choice like this, these are 2 different structures. Which one? As a matter of fact, let me replace this one with a lone pair. Why not? All right, let me replace this with a lone pair. That way they're not equivalent structures. Okay, which one would you prefer? Well, this has 6 domains. 1, 2, 3, 4, 5, 6. 6 domains, okay? Well, what's the rule that I just gave you? 5 domains on the equator, 6 domains axial. So what do we got here? We got 6 domains. Which one's axial? This one right there. This is on the equator. Now, if you were to look at this in terms of bonded, lone pair, what would you have here? You'd have bonded would be 1, 2, 3, 4. Bonded lone pair would be 8. Lone pair would be 0. Okay, because you got 1, 2, 3, 4, 1, 2, 3, 4 from the bottom. Okay, and over here, bonded would be 1, 2. Let's see, 1, 2. What would it be? It would be 1, 2, 3, 4. It'd be 4. And then lone pair bonded would be 1, 2, 3, 4. It'd be a bunch. It'd be 1, 2, 3, 4. It'd be 4. And then lone pair would be 1. And this is bad. Lone pair. Okay. And it's almost a point where I've done this so many times, I can barely draw the second one because my pen doesn't want to do it. All right. This is how I learned. This got six domains, you go axial. 5 domains, you go equatorial. You learn it at the University of New Orleans. They'll tell you, minimize your don't ever have lone pair interactions, and minimize lone pair bonded interactions as well, and try to maximize your bonded. All right, which one do you like better? I personally like just counting up. If I got 5, put them on the equator. If I got 6, put them on the axial. That's the way I prefer to do it. You do it either way you want to. But this is what you have to do for the lab, okay? But keep in mind, when you're doing the lab, what are we looking at? We're looking at 90-degree interactions. 90-degree interactions. And it may be useful to, if you have a model set. Most people don't. I have a model set. I'd let you borrow my model set, but we're not in class. All right, so that's what we have. All right, okay. So that's how you do that. So that's for the lab, and only, like I said, for this stuff right here, this stuff over here, you'll do it for lab, and that's it. Okay, you'll never see it again in your entire career. All righty, now, now, when we do this, let's say we have water. Water is a great example. And we're trying to predict bond angles. And bond angles are things that can be measured. Okay, so we have this water molecule, which is bent. And you would say that the angles should be 109.5 degrees. They should be. But you go and measure it, and you find that this bond angle right here is closer to 107. And you go and measure this angle right here, and you say this is closer to, say, 112. Closer to, it's not exact, it's different, but the bond angle between those hydrogens is less than 120. I mean, less than 109 and a half. Sorry, I was thinking about something else. It's less than 109 and a half is my point. The reason is because these lone pairs repel each other, but they repel more than the H's. They repel more than the H's. And that's the reason why. And the way I like to look at it is lone pairs take up more space. All right, remember when I said about, this hypervalence and why did they do it, and, de-expanded, and really it's about taking up space. Well, it's the same thing here. The lone pairs take up a little bit more space than the hydrogens. So they push out a little bit more. Okay, and if they push out a little bit more this way, well, guess what? They're going to push a little bit more in this way. Okay, so you end up with an angle that's still around 109. It's not like it pushes it down to 90. Okay, it's still in the ballpark. Okay, but it will change the bond angle a little bit. Okay, all right, now we have these bond angles and we have these geometries. Now we're going to switch gears just a tiny little bit, and we're going to look inside molecules. We're going to look inside molecules. So let's take a look at this molecule right here, and I'm going to draw let's draw like this. Let's draw this guy out just like that. Okay, we have this molecule here. Not important what it's called, but we have this molecule. And it's an organic molecule, which means it has carbon with hydrogens and so forth. And this is an organic molecule. And I want to know, what are the bond angles all the way down this thing? What are the bond angles? So the goal here, what's the goal? What are the bond angles? This is my goal. Now, when we have organic molecules, we look at the number of domains. We ignore, so here's some of my caveats here. Ignore bonds. or should I say number of bonds? Okay, and we just look at how many's bonded. How many? And if we have 4 things bonded, it's 109 and a half. If we have 3, it's 120. And if we have 2, it's 180. Okay, and this comes back to page, whatever page that was. It was page 350. Okay, this goes back to page 350. You have so many domains. Here's the bond angle. So let's take a look at now. We're just interested in what's the bond angles around the carbons. And this is a first approximation, okay? We're going to get more detailed in just a second, but here's my first approximation as to what are the bond angles, all right? Everybody with me so far? All right, so here's how you do it. Take a look at this first carbon. I'm just going to number this carbon number 1. All right, just to number it, just to give it a number. First carbon, because this is the second carbon, here's the third carbon, here's the fourth carbon. And I want to know what the bond angle is around these guys. Okay, so what's the bond angle? From here to there. And you may say to yourself, Mr. Pierce, I've got this. I love it when students tell me that. Mr. Pierce, I have got this. Just get out of the way. It's 180 degrees. And you will say, I got this. That's 180 because I have eyes and I can see, and you would be wrong. It's not 100. Remember what I said about Lewis diagrams and all these things? These things are just to tell you they're representations, and they're to help you see how many lone pairs, how many bonded, whatever that you have. And so what do we actually have here? We have 3 bonded. We have 3 bonded. What do we have for 3? 3 bonded. 1, 2, 3. You got to look at everything around it. What's 3? So this is about 120 degrees. I know I drew it as being 90s and 180s, but so what? It's a representation. So what? It's 3 things bonded that makes it 120. How about over here? Just to make things interesting, let's go from there to there. You know, it doesn't matter which way you go, really. What do we got here? Once again, we've got, here's 1, there's 2, there's 3. That's 120, about 120. How about right here? How about from here to there? Well, in this case, we have 4 things. We've got 1, 2, 3, 4. 4 things. What's 4? 109 and a half. It's about 109. How many do we have here? Well, here we have, let me switch colors. I'm running out of colors here. I wish I could have more colors, but here's 1 thing, there's 2 things. What is that? 180. 180 from there to there. Okay, so you got to count what's around it. You got to count what's around. Okay, let me draw another molecule here because this one's gotten pretty busy in a hurry. All right, so let me draw another molecule. And our goal is to figure out what are the bond angles around it. So let me draw another chain. All right, and remember, 2 is 180, 3 is 120, and 4 is 109 and a half. Just a reminder. So carbon number 1's numbering from the left. That would be what? 109.5. What would be carbon number 2? Let's say from here to there. That would be still on carbon number 1. That'd still be 109.5. How about from here to there? Well, now we have 3 things attached. Remember, I'm ignoring the number of bonds. I'm just looking at how many different things do you have attached, and this is about 120 because you got 3. Same thing here. We still have 3. Still have 3. That's 120. Make sure we're not. Let's see. Lock meeting, unlock meeting. Okay. All right. And we look over here. Now, here's the tricky part. Now, look at that oxygen. Here's the tricky part. You would look at that and say 180. I know you would. But look here. I've got around this guy. Let me change colors here so to emphasize. But look here around this oxygen. Okay, because we've already determined this is 120 here, and we've also determined this is 120 there. Okay, but look around, look from here to here. We're going to go from here to there. I have 4 domains, but I have 2 bonded, 2 non-bonded. That's 4 things. It's 109.5. Lone pairs still count. Lone pairs count as things. Okay, they do count as things. So we got 4 things. So the bond angle between that oxygen and the hydrogen, or the oxygen and the carbon, between the carbon and the hydrogen on the oxygen, the bond angle is still 109.5 either way. All right. All right, now let's add some nuances to this. Okay, remember what I said? These are to get you the first step. Now we got to take it, and we got to take it up another step here. And so we're going to leave this up here for a moment, because I'm going to go back and we're going to change the bond angles to be more closer to what they actually are. Because we're sciencey types here, so we're going to start with the basic, and then we're going to add on to it just a little bit. So let's say we have this situation right here. All right, and that's 3 things. Y'all see that? It's 3 things, right? And you would say that these bond angles, all 3 of these bond angles, should be 120 degrees. Everybody agree? Should be. There's 3 things. But what do we have here? Here we have 4 electrons. Here we have 2 electrons. Why did I say 4? Because it's a double bond. Every bond requires 2 electrons. So if you got 2 bonds, that's 4 electrons. The carbon-hydrogen bond is a single bond. How many electrons in each bond? 2 electrons. All right. So, and we have 2 electrons here as well. So the repulsion between the 2 electrons is less than the repulsion between the 4 electrons and 2 electrons. Because remember, it all comes down to Q1, Q2 over D, right? Number of charges. So actually, this guy right here, the hydrogen will actually be a little less than 120. And this right here would be a little more than 120. Because if you got more repulsion, it's going to push these guys apart. If you have less repulsion, it's going to push these guys together. All right, everybody with me? So let's go back on this molecule up above. Knowing what we know now, let's fix these angles. Let's fix them. All right, the first one, carbon, hydrogen, carbon, hydrogen, carbon, carbon. We're going to leave that at 109. That's good. How about over here on carbon 2? So this repulsion here and there will have a tendency to open up this angle right here. So this one should be a little bit more than 120 because we have this interaction. These two that I marked in red are 4 electrons, 2 electrons. And this interaction I'm fixing to put into green here, this is the 2 and 2. And so this should be a little less than 120. Just a little, okay? Same thing over here. This bond angle right here should now be corrected, should be a little less than 120, shouldn't it? Because this angle right here, double bonded, single bonded, should make this a little greater than 120. Do you see that? You got to look at what's next to each other. And so we're correcting these, and same thing here. This one in blue, we're going to say this is going to have to be a little less than 120 because this is pushing apart up here. And these guys over here, these lone pairs are going to take up a little bit of extra room. So I'm going to say this is just a little bit less than 109 because remember my example with the water? All right, same deal over here, isn't it? Yeah, and so this should be a little less than 109. And so sure enough, this bond over here should be a little less than 109. All right, so you got to be mindful. You have to be mindful of these double bonds. You see these double bonds? You got to be mindful of these double bonds next to single bonds. Your first approximation was 120, but you have to go in here. And you have to look at that and say, you know what? I've got 4 electrons interacting with 2 electrons. That's going to tend to push them apart a little bit more so than the single bond down here. Okay? You have to be mindful of that when you're looking for more precision. How many decimal places can I go out? That's precision, right? Accuracy is how close you are to the true value. Precision is how many decimals you can go out. So we can go a little bit further out with our understanding if we take into account the interactions. So let me draw up one more. Okay, just to show you how this goes, because it gets busy in a hurry. Okay, it does, I'll guarantee you that. But let's say we have this right here. By the way, this is called an acid group. That's an acid. All right, and let's say we had, oh, why not? Let's put another double bonded there. And let's make that a triple bond. There we go. What would be the bond angles? All right, what would be the bond angles? And so I look here, from here to there. Well, that's bonded. This carbon right here is bonded to 2 things. That's 180. There's nothing for me to correct as far as, double bond, single bond interactions, whatever. They're as far apart as they can get no matter what. And same thing here. From there to there is also 180. How about from here to here? Remember that single bonded, double bonded interaction is going to tend to push it together. So this is a little less than 120. Same thing here to here. That's going to be a little less than 120 as well. And don't forget about these lone pairs. And if I look from here to there, it's going to have a tendency that those 2 lone pairs are going to have a tendency to squish that bond together. So it's going to be a little less than 109, a little less because of the lone pair interactions. All right. So if you're just looking just to say, what's it about? You would say 180, 120, 120, 109. That's what you'd say. But if you're looking for a little bit more nuanced bond angles, then you would say, it is 180, but you know what? That carbon-carbon bond with that double bonded oxygen, it's actually a little less than 120. And the same thing with the carbon hydrogen on that acid. The bond angle there is not quite 109. It's going to be a little less than 109. Now, why would you say this is important? Well, if you're designing a drug or something like that, a change in a degree or so in a bond angle can make the difference between something that will cure something that you have or damage your brain. So, a degree can matter. A degree can matter. Okay. All right. So, next time we're going to continue on this vein here. We're going to do molecular polarity. Okay. And we're going to pull everything together on Friday. We're going to pull everything together. We're going to be able to do, we're going to name it. We're going to get the geometry. We're going to get the Lewis dot structure. We're going to get the bond angles. We're also going to do something called, and we're going to say whether it's polar or not. And then we're going to do something called formal charges. Formal charges is really the next big thing that we need to do, okay? All right, so that's what we're going to do. So let me go ahead and stop recording. Stop and stop. Let's see, let me find that. There it is. Stop, stop. There it is. Okay, so I stopped recording. So any questions before we break for the day?